Okay, welcome to today's lecture on DC motor control. Now, in the last class, we looked at stepper motor control and also then we looked at servo motor control. Now, after that, we are looking at the DC motor control. Now, the DC motor is controlled by using encoder, a position sensor, which is attached to the rear of the motor. And we can, as we rotate the encoder, we can see the encoder pulses coming out. Okay, so that's the first task that we have today. The second task is to control the speed of the motor. Now, how do you control the speed of a DC motor? We can control the speed by changing the voltage. So if I increase the voltage going to the motor, the speed will increase. If I decrease the voltage, then the speed will decrease. And how do we increase and decrease the voltage? By increasing the using the PWM of the Arduino microcontroller and increasing the pulse width or decreasing the pulse width. So if I increase the pulse width, more voltage and more speed. Okay. Now the third task is basically PID control. So we'll be looking at the PID control part, where we are going to put different gains for P, I and D and then see how the system behaves. For example, does it overshoot the position desired? Does it not reach the position? Is the system response underdamped, overdamped, and things like that. Okay, so let's start off with the first part of our experiment, and I will explain the manual first, okay, what we are going to do, and then we'll see the actual experiment and the program. Okay, so this is the DC motor with encoder, today's experiment. And what we have, the various materials that have been supplied, one is the Arduino Uno microcontroller board, then we have the motor driver L298, and then we're having the various batteries, battery for power supply, and we are having wires for connection. Okay. Now, the first part of the experiment, let us come here, is reading the encoder signal from the Arduino. Okay, so what we are doing is we'll move the encoder and then we'll see how the encoder, the signal from the encoder, that is the pulses from the encoder, are changing as we are rotating it by hand. The second is calculating the velocity of the motor in RPM. That is, what we are going to do is we are going to change that. We want to calculate how much is the motor velocity in RPM. Okay, and third is controlling the motor using PID technique. So this is the first experiment where we are going to connect the DC motor. So this is the DC motor and it's connected directly to the Arduino microcontroller. So there are 4 wires. One is going to 2, 3, then 5 volt and ground. So 5 volt and ground are the power, and then you have 2 and 3. And 3 is the PWM pin. Okay, so we are using the third pin for PWM signals. So this is showing what we are trying to see is that when we run the program and we rotate this by hand, so this is the magnetic encoder which is shown fitted at the back of the motor. So when you're rotating by hand on the scope, what you can see is the output, and these are the magnetic encoder pulses which are coming out. So as you're rotating, it is also giving the pulses out, which is showing that the encoder is rotating now. Okay, so this is a magnetic encoder, and there are 2 outputs, A and B there now, having 2 different colors. Okay, so let's open the first program. Okay, this is the first program, which is basically to read the encoder. As we are rotating the encoder by hand, we can read the we can look at the various pulses coming from the encoder. Okay, we see it here, right?
Yes.
Okay, so let us connect. It is connected. Then what we do next is we are going to upload the program. Okay, so this is the serial plotter. Okay, so now let us look at the connections of the motor. Okay, so this is the DC motor. Now you can look at the DC motor here. So in the front side, we have connected as usual with a protractor and a link which is connected. So when it rotates, you know how fast or how slow, or in terms of position control. So this is the DC motor here. And in the DC motor, what we can see is that this is the DC motor part. Okay, this is the DC motor part. This is the gearbox in front. And at the back, there is an encoder. That one there is a magnetic encoder, okay, which is attached to the DC motor shaft. Okay, so when I rotate this encoder, what will happen? The motor will rotate. Okay, so you can see that by rotating, that when I'm rotating the encoder from here, because of the gearbox, this is moving also. The link in front is moving, but slowly, because there is a gearbox in that. Okay. Now this is connected to the microcontroller as shown there. So this is showing the microcontroller connection. So 4 wires from the motor are going there. Okay. And this is the connection to the back of the encoder. This is the connection to the back of the encoder. Okay. So now what we'll do is you can see the output when we are rotating. You can see there is that blue line and the red line. Okay. These are the value 1 and value 2 of the encoder that is coming. Okay. So when we are rotating, depending on how fast we are rotating, the square waveforms are being generated. Okay. So when we are rotating by hand here manually. Okay. So when we are rotating this by hand, what we are seeing is that the waveforms, the blue waves and the red waves, not waves rather, these are square waveforms. Okay, the square waves of are being formed as the encoder is rotating. Okay, now you can count how many of these are passing through and how much time it takes. That gives us the basic velocity. From there we can find out by also including the gear ratio in front of the motor. Okay, so this one was basically to see how the encoder behaves. So maybe we can stop rotation and then see that the moment you stop the rotation, you can see that this is also stopped. Okay. Now if you rotate in the other direction, reverse the direction. Now if you reverse in the other direction, then again it has started. Okay. Okay, so we have two, channel A and channel B of the encoder. So how many square waves are coming and in the time and how much time? Based on that we can compute what is the velocity of the motor.
Yes.
Okay, we have now opened the second task in which we are measuring the velocity of the motor. So what is seen in this program here is that this velocity is given by this. So what we do, there is a set motor function which is shown in line number 52. Okay, and in line number 52, so okay, so we have opened the set motor function. We have opened the task for number 2, task number 2, and there is PWR which actually controls. So in line number, what line number is this? Line number 51. There's a PWR which is actually giving the number, and this PWR is passed on to the set motor function. Now the set motor function contains this 5 elements. The first one is the direction, second is the PWR which corresponds to the PWM value later on in the set motor function. So by changing this PWR value, we can change the speed of the motor. Okay, that is basically changing the PWM pulse width of the motor. Okay, in some particular ratio. So that is what we are doing here in this experiment. Now let's look at. Okay, so we have opened the set motor function. We have opened the task for number 2, task number 2, and there is PWR which actually controls. So in line number, what line number is this? Line number 51. There's a PWR which is actually giving the number, and this PWR is passed on to the set motor function. Now the set motor function contains this 5 elements. The first one is the direction, second is the PWR which corresponds to the PWM value later on in the set motor function. So by changing this PWR value, we can change the speed of the motor. Okay, that is basically changing the PWM pulse width of the motor. Okay, in some particular ratio. So that is what we are doing here in this experiment. Now let's look at the motor. So this is the motor as usual. Okay, the back of the motor there is an encoder. Now this is enclosed, we didn't open it, and in the front there is the link which is connected on the protractor. Now this is a power amplifier. There is a power amplifier which is amplifying the motor currents which are being given to the motor. Okay, because the microcontroller can supply very small amount of current which is not enough to drive this motor. Okay, and hence we are connecting it with a motor power amplifier. Okay, so this is the connection diagram, okay, for the Arduino microcontroller, which is connected to the power amplifier, and from the power amplifier it is connected to the motor. Okay, so that is the motor connection in the back of the motor. Okay, now let us run the program and see. So you can see that I have run the program and it is rotating at a particular velocity. Okay. Now how is it working? Basically, the Arduino microcontroller is generating a PWM signal, which is going to the power amplifier, and then depending on the pulse width of the signal that is coming, there is an average voltage that is coming in, and that average voltage is going to the motor, and the motor is rotating based on that. Okay. So there is a calculation in the program. Depending on the gear ratio, the velocity is being controlled. Okay, so suppose I want to decrease the, let's see, this is my velocity, okay, in RPM we can say. Now suppose I want to decrease it, what I can do is I can make it 25. So I reduce it to half. Okay, so I make it half now. And I press enter. Oh, it is too slow for the motor. Let us then increase it to 100. I have increased that value to 100 now, and I download it. So you can see the speed has increased. Okay, so it has become 2 times the speed. Okay, so we can change the motor velocity by changing the this number which we are inputting there. Now this PWM number corresponds to the PWM pulse width, and there is a calculation later on in the program if you see a little bit later. Okay, so there is a motor. So it also displays what is the speed. Okay, so if you look at the program carefully, we can control the velocity of the motor, and which is a function of the gear ratio and the encoder counts per revolution. Based on that, we can compute the average velocity of the motor. Okay. Okay, so that is our second task, controlling the velocity of the motor by using a PWM signal. Okay, so we do the next task, that is position control using PID controller, in which case the same setup is there. We have the DC motor connected to the encoder at the back and with the power amplifier, and then connected to the Arduino microcontroller. That was done in the previous task. And this is the program that we have uploaded for the PID position control using PID gains, okay, different gains. So here we can see that this is the pin modes have been written. Okay, the various pin modes have been written as the input pin, output pin, which pin, PWM pin. And then as we move down, you can look at line number 58, 59, 60. So that gives the values Kp, Kd, and Ki. Okay, so by putting different values of Kp, Kd, and Ki, we can see a different response of the system in terms of position control. Okay, so this is the complete program, and this complete program basically makes use of PID control system or PID controller structure, in which we have an encoder, we have the power amplifier, and then by putting different values of the gains, we can basically control the response of the system for position control. So first let's start off with 300. Okay, so this is the program, and we can see the set target position, which is indicated on line number 54. Line number 55, it says 2400. Okay, so what we'll do is we'll look at the we'll track and see how that setting only. And if you look at the gains now, let's look at the gains. So KP is 3, KD is 0, and KI is 0. So it means that this is only a proportional controller. Okay, let's see how it behaves. So this is the same setup that we have as before. So this is our DC motor with the encoder at the back, and this is connected to a power amplifier and then the Arduino microcontroller. Okay, so this is same setup as before. Okay, so now let's what we can do is let us compile the program and then run the program and see how it behaves. So what you can see is that the set position was the blue line, okay, and the way it has behaved from 0, it has gone up. The red line, it has oscillated a little bit, and then it has gone and set to the set position, which is shown here. You can look at the numerical value also. It is showing 2400 and it's 2401. So it's almost there. Okay. Now in the second part, what we'll do is I will change the gain. So the second gain is the KD gain is there, 0.05, 0.5. The integral gain is still 0. Okay, so there will be some error at the end of the day because integral gain is 0 now. Now what we can do is we can again run the program. So I compile the program and I run it. So what we can see is that again, now if you look at, there was a derivative gain. So what would happen? The oscillations are much lower. You can see that it has slowly risen. The red line has slowly gone up, and then it's meeting the desired value. Okay, so this is the result of the derivative gain. So very clearly it shows that there was the derivative gain, which was basically proportional to the error. So it reduced the oscillations of the system. Now in the third case, let us put the integral gain, which is 0.05, and let us run the program again. Sorry, compile and then run. Now there's an integral gain also, proportional, derivative, and integral gain. So you see that there is no oscillation, and it has gone very, very close to where it is supposed to go, 2400, 2402. There is a very small error there. Okay, so this experiment basically shows us that the effect of changing the gains on the PID system.